Hello, we are going to look at exponential growth and decay models. The modeling of exponential functions is great because we could talk about all different kinds of situations in real life, whether it's money in a savings account or the depreciation and value of a car, or maybe it's half-life or radioactive decay, all sorts of things, population growth, so many ways that we can model the world around us using exponential functions. So what I'm going to do here is we're going to talk about growth on one side and decay on the other, and you're going to want to have your calculator or Desmos handy for this because we're going to need it to solve some of these equations. So when a function increases over time by the same factor here meaning rate that we are multiplying, it is considered exponential growth. Now, there's a lot that should look familiar to you in this equation or this formula here. So f of t is equal to a. A is doing the same job that it has been doing when we talked about just exponential models in general or exponential functions in general. It's our y-intercept. And you will recall that the y-intercept happens when the input, in this case t, is equal to 0. And so what if we're talking about this as a function of time, when time is 0, like we haven't had any days or weeks or months pass yet, that's going to tell us the output that corresponds with it, which will be known as our starting amount. Since we are not dealing with negative time. All right, next we have R here. R is going to be our growth rate. And this is usually given to you as a percent, but you'll need to convert it to a decimal to be able to use the formula. So usually this is like 10%, 5%, 8%, something like that. Last but not least, here we have t. Notice, right, f of t, that means that we're dealing with functions of time. We're plugging in time and popping out whatever the amount is that is growing. And so t here stands for time. And this whole expression, right, 1 plus whatever that rate is the decimal, so like 1.07 for 7% growth. This is known as the growth factor because this is the factor you're multiplying by over and over and over again, right? It's the base of our function. All right, so if we think about what this looks like graphically, because that base is always greater than 1, it's going to increase like this or grow. Remember, this x-axis shows us t for time. And this part right here at t is equal to 0, that is a, our starting amount. All right, so let's talk about some models here. Mr. Benjamin has $500 to put into his savings account. That's a starting amount. And it's going to earn interest at a rate of 1.3%. This is not a good interest rate for his savings account. He's not really going to make any money off of this, just so we're clear. So you'll see it's kind of depressing. All right, anywho, write an exponential model for this situation. So it's going to look like f of t is equal to 500. That's our starting amount. Times 1 plus, we have to turn that into a decimal. So it would be 0.013, right? Because I moved the decimal place 2 to the left, or I divided by 100, whatever makes the most sense to your brain. And that is raised to the 10th power. All right, so if I want to know what the balance is going to be after 4 years, that's a t value. So what I do is I'm going to plug 4 into my function for t. And so I'll be 500 times 1.013. I just went ahead and added it myself. You can plug it into your calculator still. It's 1 plus the decimal though. All right, and then you can plug that whole expression into your calculator. And I'll get out about $526.51. So like I said, after 4 years, not growing a whole lot. Now, if I want to know when the balance exceeds $800, what we're thinking about here is if I graph this, it's growing, right? I want to know if the output or the y's is the amount of money. So I want to know when y is equal to 800, when these cross over that t value, I want to know what that t value is. So what we'll do is in your calculator or on Desmos, you're going to graph in like y1 or as your first equation, you're going to put 500 times 1.013 to the x power because it doesn't take t. And then your other one will be, you're going to find what, put y equals 800 and you're going to see where those cross over. So let's go ahead and graph that. All right, so let's graph this equation for Mr. Benjamin's car. So I'm going to type in y is equal to, actually the great thing about Desmos, you don't even have to put y is equal to, you can just start typing in the equation. So we're going to have 500, 1.013 to the xth power. And then we're going to have y is equal to 800. And I know what you're thinking, Kaylin, I don't see those on here. And you're right. So what we need to do is, one of the many reasons I love Desmos is I can just pinch and drag. There's my equation, there's my model starting at 500. And now I can see where they intersect. And so if I just click right there, Desmos is pretty smart. It says, I bet you want to know where these intersect. And so that intersects right there at 36.38862. And we can round to the nearest whole number, which would be 37 years. All right, so we found that this will happen after t is about 37 years. We'll round to the nearest whole year. Awesome. Well, just like things in life can grow exponentially, things can also decay exponentially. So let's look at that. When a function decreases over time by the same factor, again, we're multiplying, it's considered exponential decay. All right, so all of the things that we wrote about our graph here, it all can be copied over to the other page because it's all pretty much the same, only some slight changes. So let's look at that. I know what you're thinking. Why don't I have an Apple Pencil? I paste. All right, and then we just perfect. When I say perfect, and then I move it at the last second. That was good. All right, so what's going on here? Well, A, still the starting amount. R, still the rates, except we're not growing anymore, right? We are decaying. So this is the decay rate, but you're still going to have to write it as a decimal, okay? T still stands for time. And so this one, notice the minus r now because we're decreasing by that 5 or 7 or 10%, whatever it is. And so that makes us not the growth factor, but the decay factor. And it's always going to be less than 1, right? Since we're taking 1 away. So if I were to draw the graph for this guy, the decaying function, so this is still t for time, the input, and where it crosses over a is the y-axis is a, our starting amount. Notice how it's just going to get smaller as time goes on. All right, so my buddy Flynn here is buying a new car for $17,000. Okay, so $17,000, that is our starting amount. The car depreciates in value or decreases by about 5% per year. Okay, so this is decaying in value. Let's write a model for this situation. All right, so what I'm going to do is we can actually, instead of writing 17,000, we're just going to put 17 in our equation and say that our equation is written in terms of thousands of dollars. That way, we usually see people doing this with like millions, right? Like 1.5 million instead of writing 1, 5, 0, 0, 0, 0, right? That just gets too big. So this is going to look like f of t is equal to 17 times 1 minus 0.05, our decay rate, and then to the tth power. So if I want to know how much Flynn's car is going to be worth, after 5 years, I'm going to plug that value in for t. So I'm going to have f of 5 is going to be equal to 17, and then this will be 0.95. Right after I subtract to the 5th power, and then you'll go ahead and plug that into your calculator of choice. Really, phone calculators have come a long way, but they just aren't, especially with complicated formulas like this, where we're looking at exponents and multiplication. They just don't really cut it. So Desmos.com, it's free. They have a graphing calculator, scientific calculator, free apps. You can use it on your desktop, whatever floats your boat. I've had it on my iPhone since 2018, I think, when I was student teaching. All right, so here we go. We've got an output, now that I've gotten off my soapbox, of about $13.15 thousand, right? So this doesn't mean that poor Flynn's car is worth $13, but $13.15 thousand. Right, this is in terms of thousands of dollars. All right, so when will the car be below 800 or 8,000? Geez. A couple things to keep in mind here. When we are thinking about graphing, like we did with the growth model, this is depreciating, right? So I need to plug in y equals 8. So the reason for that, for using y equals 8 instead of 8,000, is remember we made our equation in terms of thousands of dollars instead of dollars, right? So we didn't have to deal with putting all those zeros in. So you're going to go ahead and, like we did before in Y1, you'll put your model. Okay, that's an X. I started writing a T and then remembered I need to write X. And in Y2, you're going to put So on TI, right, there's some extra steps. Everything that we know and love lives under second calc. Um, um, but right, the trace button, you'll want to select intersect and follow the prompts there. And then on Desmos, all you have to do really is pinch the graph to find it, which is pretty cool. So I'll insert here me doing this on Desmos. All right, so we're back to graph something else. So let's get reoriented here, kind of by the origin. All right. Now we're looking at Flynn's car. So I'm going to show you what it looks like without putting y equals for that. Sorry, it just feels like a superpower. So I forgot to hit my exponent. There we go. So 17 times 0.95 to the x power. And then we're going to look at when y is equal to 8 for 8,000. All right, so there's y equals 8. And then here you can see the green function is the value of his car. That's our model. And here we can see them crossing over at the point 14.695. See what I did there? 3. So, yeah, that would round to about t is 15 years. There you have it. All right, so we ended up with t is about 15 years. All right, so let's go ahead and think really quick about the following models. So are they growth or decay, and how do you know? So there's a lot going on in these formulas, but the only part that we care about, right, is this factor here. And if it's greater than 1 or if it is less than 1. So go ahead and tell me what you think. Make sure you are explaining your thinking. All right, so this first one is decay because that factor 0.87 is less than 1. This guy here is growth because 1.2 is greater than 1. All right, there you have it, folks.